First of all, I'd like to introduce Dr Eunice Lo. So Eunice is a climate scientist here at the University of Bristol. Her research is very much on the interface between climate change and health, looking in particularly around extreme weather events and their impacts. Eunice's work utilizes both climate, weather observations, large ensembles and simulations, but also integrates statistical health models, thereby actually creating a relatively unique skill set that actually brings epidemiology and climate science together. So, Eunice, over to you. You have 20 minutes, but if you can be quicker, then we might need the tea break.
Hi, everyone. Thank you for the introduction. I'm going to just jump straight into the talk then. So my talk is mainly about extreme weather and its impacts on health, with a little bit of AI, because that's not actually my expertise. So my expertise is in descending order: extreme weather, and then health, and then AI. But yeah, I do work in mainly extreme temperatures and have a lot of focus in the UK. So hopefully this will be a talk that gets us thinking about how we can apply AI methods into this space of interdisciplinary research as well. So this is the model that a lot of the research that my group and I do. We use this kind of model. So basically, we have a lot of data in weather and climate. It could be daily data, for example, in the very hot period in the UK in July 2022, we would have daily maximum or daily average temperature of each day, right? And also from death certificates and other records in health, we also will have mortality records for every day. So how many number of deaths there were per day in the period that we're interested in. That's just from all causes. But in my research, we want to understand what is the mortality impact, for example, or other health outcomes, their impacts from exposure to extreme temperatures or temperatures that are not optimal for the human body. So what we do is then we use models developed by epidemiologists to run regression analyses on this large number of data, usually on a daily resolution. And then we try to find a relationship between exposure to temperature and also the risk of human mortality, which is on the right here. These kind of models then also can take in a lot of other data. For example, if we're exposed to very hot temperature today, doesn't mean that people only have the effect in their health today. It could mean that they have the health impact, up to a few days later. If it's exposure to cold weather, it will be probably a few weeks later that we still see a mortality impact from exposure to cold. So we then do kind of like a distributed lag nonlinear modeling, again developed by epidemiologists, to shift either the temperature or the death data by 1 day at each time to then do the regression on them. So we take into account a lag period of up to 3 weeks if we're talking about mortality. And we have lots of data to construct a model like this. So this is real data actually for Southwest England. I chose this period because the 19th of July 2022 was the hottest day on record, 40.3 degrees Celsius in the UK. But obviously the daily average temperature in the Southwest was lower than that. And doing the regression analysis gives us a curve like this. So it gives you the mortality risk on the y-axis at different exposure to temperature. And we can see that we get increased mortality risk for cold temperatures, but we also get increased mortality risk for Southwest England and also other bits of England and the UK in hot temperatures. And this kind of modeling then formed the basis of a lot of our research, which we look into what about a world without climate change, which will be a counterfactual world. We look at the extreme weather statistics in that, but then we can apply a temperature health model that's based on the observations to different things, and also to different time periods, for example, in the future when we project into what would be the heat health impacts in future climate change under a very high 4-degree scenario, for example. But a curve like this needs a lot of data to go into it, right? So this curve was done by the regression modeling based on daily data for every day in the period 1981 to 2022. So about 40 years of data going into it to give you a curve that's quite constrained without a big uncertainty associated with it. But for a lot of places, we simply just don't have the data, mainly because we don't have daily, high-quality health data for a lot of the countries in the world. And this is a graph made by Dan Mitchell a few years ago. So the orange regions are where we don't have daily mortality data in the world for this kind of research, let alone 40 years of this data. So these are also places that you see is large parts of most of Africa, places like India. These are the places where we project to have the largest population growth in the future. So these might be the places where we expect a lot of health impacts, but we just don't have the data to construct the temperature mortality or temperature other health outcomes models based on the statistics because we don't have enough data. So one thought is that in terms of AI, can we train AI models? And I'm not an expert in AI, but can we train AI models based on the data, including large data sets from climate, large data sets from health, large data from places, socio-economic background or demographic characteristics of different places, from places that we have data, and then predict these kind of relationships for places that we just don't have the statistics to construct the statistical model, but could learn something by us training some AI models. So this is something that I'm thinking about, haven't done anything on it, but thinking about with some computing colleagues who are great at AI to hopefully develop. So if you want to chat about it or teach me anything, then please come and chat with me. The second bit of this talk I want to talk about is not the quantitative stuff, but the qualitative stuff. So this is work that I led with children of the 90s, aka ELSPAC, that Leon talked about. So in addition to, say, daily mortality or daily hospital admissions from the NHS, those are quantitative data, we have a lot to learn from just general people who actually, all of us, experience extreme weather and what our actual experience is during those extreme weather events. So I partnered up with Children of the 90s, which is this Bristol-based large health cohort. They started in the 90s, recruited over 14,000 pregnant women at the time, and also subsequently their partners. Obviously, it's been running for 30 years, so it's now the children of the 90s are now in the 30s. These people, some of them have children, so it's 3 generations of people, a lot of them still participating in this large cohort study, where they send out annual, if not more, questionnaires to the people about their health, well-being, and lifestyle. And I think a lot of them at different stages in their life, for example, children do go into give some samples in their clinics and so on. So this is a massive asset based in Bristol, but they never asked them what the experience of extreme weather was. So we started new rapid surveys about extreme weather with ELSPAC, but also we utilized some JGI data science to help us understand the data that we've gathered, because it's a lot of data, and especially on the qualitative data is a study in itself to understand how we can then pick out themes from what people wrote in the surveys. So what we did was that, first of all, we sent out a survey just about a specific heat wave in September 2023. That wasn't the hottest thing ever in the UK, but it was quite out of season in September. It was a week where, for 7 consecutive days, there were somewhere in the UK recorded over 30 degrees Celsius, so relatively hot. So we sent out a standalone survey to the ELSPAC cohort, asking about their physical exercise, their access to healthcare, their moods, appetites, sleep, productivity, and all sorts of other things during that period compared to the normal. We also wanted to know whether people knew about the heat health alerts by the UK Health Security Agency at the time, and then what they did about it, if they knew about the alert. So that's actually, I'm not going to talk more about the heat one now, because it's now been published in environmental research letters by Joe Godwin. But subsequently, we also sent out another survey about a cold and stormy month in January 2024. So that was a very cold period. In England, temperatures fell to about minus 11 degrees Celsius in some places, but also there were back-to-back storms. I think it's storms Hank, Isha, and Jocelyn in that period. Many flood alerts. So we sent out only one survey asking, so 2 sections, one about the cold weather, one about the stormy weather. Again, asking about the experience and did they know about alerts, what they did about these alerts. So I'm only going to talk about the cold lived experience here. So we basically had a section about the many different aspects of the life in terms of physical health, activity, sleep, etc. And then asked them to rate, is this a lot worse than your normal, slightly worse, no change, better, etc. So these are the numbers. We've got 2,736 responses for this survey, and this is one summary graph of that. So you can see that just looking at the colors, for all of our aspects of life that we asked about, there were more adverse impact that people reported than positive impact during the cold weather. In particular, we've got about 50% of people saying that they did less exercise during the cold period, probably because they stayed indoors more and couldn't do the usual things. And also about over 45% of people said that their mood was either slightly or a lot worse than normal. And these outnumbered the positive. We also had some no changes or not applicables because, for example, they didn't work or etc. But you can see that also perhaps these might be linked because people might reduce physical activity or exercise because of wanting to keep warm, but then perhaps it also affected their mood. So these things are probably quite linked. And what we could tease out more in this kind of categorical data is what they wrote in the surveys, in the text responses. And also we wanted to understand what they did during the cold weather to kind of adapt to the weather. So these are some of the text responses that I got. These are not the real ones because I had to anonymize them, but it kind of convey the same message anyway. So we don't know who they are because it's all anonymized by Elsbeth themselves, but a lot of people said they cancelled plans or they put on the heating more or they prepared the car or didn't drive and changed their plans and so on. And we have got thousands of these responses in different bits of the survey. And we really wanted to find themes of what are the major adaptation actions that people took. But this is quite challenging if you want to hire a researcher to read through thousands and thousands of lines of text. A lot of them also say, see the above question or left it blank, or they mentioned many things in one big paragraph. So we thought that we would actually work with JGI, which is the Data Science Institute here, to try to use kind of natural language processing to tease out topics using topic modeling. So this is what Hugh, in particular, worked on this project with me on this topic modeling. So he used a bird topic, which according to his expertise, was better out of the other packages that were out there. It's all done in Python, I think. So this is, in general, the flow of what we did. So first of all, we had to pre-process our text data because some people wrote many things in one sentence. And the shorter the sentences are, the better it is for the BERT model to pick out topics. So we removed the blanks, we split the sentences by commas, full stops, and other things. And then, because it's text and it's quite hard for the model to understand how to cluster them into different groups, but it would be much easier if we converted it into different numerical representations, which are basically vector formats in a multi-dimensional space, and then cluster them. So we use some sentence transformers to convert these into vectors in a massive space of many hundreds of thousands of dimensions, but that's too many. So then we reduce the number of dimensions, as in, say, if we had if only we had a 3-dimensional data, we kind of reduce it into 2-dimensional, but this is a much larger number of dimensions that we were dealing with. And then after we reduced, so we vectorized our text, and then we reduced the dimensions, and then based on the numerical representations of these vectors, the models can then sort the data into different clusters. After that, based on what was in these clusters, we can then pull out different representations of different clusters. But in doing that, we also have to exclude a lot of words like I did this. I wasn't a very good representation of any action that is about adaptation to cold weather. So we excluded some pronouns and prepositions and so on in that to pick out representation of each cluster. And then finally, based on the representations, we can then kind of see which words appear more frequently. Say if one word appears really frequently in cluster 1, but not very frequently in cluster 2, then perhaps it is a good representation of what the topic means in cluster 1. So then we found good representations of each cluster. So basically, this is a workflow in BERT topic where we had thousands of free text responses. We shortened them, turned them into vector formats, and then clustered them, and then found found some words that represented each cluster. And these are all because we wanted to find what people did in terms of adapting to cold weather. Right, so this is one of the raw results that Hugh sent to me. So he ran all the models. And also, I want to say that this modeling allowed for a noise cluster, so anything else that it couldn't put into one cluster, then it was kind of a noise thing, and it was -1 there. So then we could count how many people talked about different adaptation actions. So in here you could see, this is just a raw output, so we did a lot more post-processing here, but the raw output gave us, say, first topic, about 500 people talked about it. It's topic 0 where people wore more clothes and warm clothing and gloves and so on. Second one, quite a lot of people said it, and it was cancelling outdoor appointments, outdoor activities and so on. So it is rather good at picking out topics. Obviously, there's some overlapping here because these were a model, and we actually ran a natural processing model on human experience, which is quite ironic, but this is what we did. And so we did some post-processing as well to perhaps combine different big topics that actually all meant people used more heating, but some people said they put the thermostat up, some people said they bought a heater and so on. That's all heating. So I did some post-analysis, but this definitely sped up how we did this analysis on free text responses in the extreme weather survey. So this is what we came up with in the end. This is all submitted to a paper a couple of weeks ago. So this is a summary graph of 2,625 actions that were mentioned by our respondents. Not everybody mentioned something. And we grouped them into, using topic modeling and also our author judgments, to group them into different adaptation actions to cold weather in January 2024. So 600 people took personal care, and we thought it was about using a hot water bottle or wearing warm clothes or having hot meals and so on. A lot of people used technology, which is heating. Quite a number of people, so 466 people said they reduced activity, either cancelled activities or exercise or playing golf, someone mentioned very particularly, or staying indoors. Some people adapted their home, made plans that are alternative to their routine, so went to bed earlier or walked the dog during the hotter time of the day and so on. And some other people took precaution to stock up food and prepare their car, etc. So by doing the topic modeling based in AI, then it sped up our analysis in these extreme weather cold survey about people's experience. So I'm going to stop here. So my summary is really that we do a lot of extreme weather and health work here and across the GW4, I'm sure, and it affects human health in many ways, right? There's quantitative analysis, which I'm more used to, and we count mortality and hospital admissions and so on, but there's also qualitative impacts that I'm quite interested in, and that's about impacts on daily life, asking people what they felt and how they dealt with it. And I think AI models can be used to complement the statistical models in the quantitative sense, but also help us to gather and also make sense of a lot of qualitative data coming from surveys that we deployed. And I hope that we'll have more rapid surveys in Ausbec in the future about extreme weather. Thank you.
Thank you, Eunice. That was great. So please, there was a lot there. A lot of really good questions, I think, can come out of that. But we're going to go on to straight away to our next talk, which is going to be given by Dr. Thomas Kjeldsen, who is a reader in the Department of Architecture and Civil Engineering at the University of Bath. So Thomas has over 20 years of research experience focusing on mathematical and statistical modeling of hydrological environmental systems, particular emphasis on extreme events, flood risk, and urban hydrology. He's led the scientific development of the current water industry standard methods for risk-based hydrological design in the United Kingdom. He's got lots of recent research. I'm not going to read through all of those. However, what he's going to talk to you about today is around enabling accessible flood prevention using explainable machine learning. Thomas.
Thank you very much, Guy. Thank you very much for the invitation to come. Initially, the invitation didn't come to me, I should say. It came to my long-time collaborator, Andrew Barnes, who's a lecturer in our computer science department, hence the title with explainable machine learning, etc. He went off and found himself a better paid job and asked me to stand in instead. So I said, yes, I can do this. I'll give it a title that actually says what this is about. And it's about using images from CCTV cameras to help local authorities manage garbage and debris built up in their rivers. So the idea behind the project, so how do I? Oh, yeah. So this is the team that's done it. So we have a multidisciplinary team, I guess. I sit in civil engineering. We had students from civil engineering, computer science, mathematics. And key as well, we had Simon, who is the flood manager from Cardiff City Council. And the reason this came about was that, of all things, I went to a meeting in Cardiff, a GW4 meeting, nonetheless, but came early. So I went for a stroll in Cardiff, and there was a guy in a yellow vest looking in a river. Being a river engineer, I couldn't help asking him what he was doing. And he was looking at his trash screen and his culvert to make sure everything was okay, and we got chatting, and that's how this project came up. So what happens in urban rivers here and there and everywhere is that you have a river here, so there's a river flowing here. Somewhere up here at the end, there's a culvert, so that's a concrete pipe that goes under a road or a housing estate or something. And during wet weather, you get debris of all sorts carried down these waterways. And what you don't want is that this debris gets stuck inside this pipe because it's dangerous and cumbersome and expensive to get it out from in there. But you need to get it out, otherwise you've effectively built a dam that causes local flooding. So people put trash screens on. These are just metal grids here to protect the inlet of the culverts. But of course, they then catch all the debris, and that's an example here. So this is an unholy mix of garden waste, green waste, plastic bags, whatever people dump in the river. Most local authorities, people drive around. They have teams that drive around looking at all their hundreds of culverts to check whether they need cleaning or not. Cardiff had the foresight to try to set up CCTV cameras. They had a grant, so they got images beamed in from key locations, but it required them to log on and actually have a look to see whether there was any debris. So they could do it remotely, but they had to go there. So the premise of our study was, if we have enough of these images, can we train a machine learning model to distinguish between a blocked and an unblocked trash screen, which, if successful, could hopefully lead further down to a system that could issue online alerts so that they didn't actually have to sit and log in and look at the images, but would just be sent an alert in case the machine learning algorithm detected a block. So we had a look at all their cameras, and they had installed them. Only very few of them were of any use, really, because they pointed in all sorts of different directions. So they got a grant to set the cameras up, but they were looking at the birds and the roads and everything except the trash screens they were supposed to look at. But there was a few that did look at them. So here's one. This is in northern Cardiff. It drains a sort of mix of urban and suburban area, and there's a lot of garden waste getting chucked into this river by people living there. And down here there's a culvert, and that's a trash screen, and if that gets blocked, there's a whole commercial shop housing district here that get flooded. So it's very important that this is kept clean. So this is our case study. We scraped all the images, so they take images, they get images every day, they look at them sometimes, and they store them and never use them again. So we scraped all the images that they had since they installed the camera, which was about 800 images of 800 to 600 times resolution. We looked through them all, well, the students did. Some of them had to be removed because of the quality, see example. Left a pool of about just short of 600 images. We then labeled them as being either blocked or unblocked. So we said, well, we thought, that looked blocked, that looked unblocked. We then checked, we sent a sample of our labeling off to the managers at Cardiff, and they came back and said, well, you say unblocked, but we think it's blocked. And actually what turns out, they were much more risk averse than we were. So we relabeled all our images. So we ended up with more blocked than unblocked images. So we have an unbalanced data set to work from. So this is examples of what's not working so well. So sometimes it lost connectivity, so you get an image like that. Sometimes there was spray or rain on top of the lens of the camera. Sometimes something like this happened. You just get a branch, a bramble sort of growing in front of the camera. Of course, to a dumb machine learning algorithm, that'll look like a block, but it's not. We also had a different case study where a spider decided to build its web across the camera, and you flash a spider. So all these sorts of things we took out in this initial trial here. And then we had to try to, okay, so how do we do it? What kind of machine learning model should we use for this? And we asked some of our experts in our computer science group. This was me asking them before we got computer science on board. And they had all sorts of ideas, from very, very sophisticated to very, very simple. And what we ended up with was a logistic regression model where you classify your images as blocked, unblocked, and then you try to fit some a model here that predicts the probability of it being either or based on some input x, where x sort of represent the image itself. And I'm sure I'm talking at an AI institute. So this is rather basic, but you have a regression model where you have an explanatory variable x, and you want to say something about y, you're trying to predict y, and you can have all sorts of values of x, and you can fit a smooth line between. But in this case here, we have something that explains whether an image is either unblocked, so that's the one at the bottom, labeled 0, or blocked up here, and it fits this sort of sigmoid curve. And based on what the image looked like, you'll end up with a probability of either being a high probability of being blocked or unblocked. That's the kind of model we fitted. So what does this look like in principle? Where here, again, we got this probability f, some parameters with x is the image. So we have an image that's made up of lots of little pixels with different colors, grayscale. We converted them into grayscale images. You take that, you flatten it into this matrix, you flatten it into a vector, and you put the vector in. And then you use your machine learning algorithms to try to come up with a set of parameters, theta here, that give you some sort of sensible fit to the data. I think these models are, to my sort of somebody trained in classical statistics, they looked vastly over-parameterized. So probably not surprising that we can find reasonable solutions, but I'll talk more about that later. But what we did was we had this unbalanced data set where we have more blocked than unblocked images. So we tried different strategies to try to say, well, how can we amend this data set? So this is a slightly complicated diagram, but here we have all the blocked images, that's the outer circle, and the unblocked images. That's our imbalanced model, that's just the raw data. We then tried to go, well, let's make let's sample from the blocked images, so we have just as many blocked as unblocked. So we throw away data, except essentially that's an undersample model. Or let's try to take some of the unblocked images and augment them in some way so we get just as many unblocked as blocked. That's called our augmented model. So we did some experiments where we tried to augment our data by adding some random noise at different levels. So here we have increasing augmentation as you go from left to right. To see if you can create this balanced data set. So we're starting with the same images, they're just sort of recreating augmented versions of them and using them in our model fitting. So we did the traditional thing you would do in a machine learning model where we take 80% of the data, we put 20% aside, select it randomly, fit the model to the 80%, try to train it back on the 20, see if I fitted a particular image, can it tell me whether this image that it has never seen before, whether it shows a trash screen that's blocked and not blocked. And we measured that using accuracy, recall, and precision. And for each of our 3 data types, so the imbalanced, the undersample, and the augmented. And what we saw from this relatively small data set was that we get sort of, for the augmented data set, we get accuracy, recall, and precision that are sort of in the range of 90%. So you give it an image, and you're pretty sure that it can identify whether it's blocked or not blocked. And I thought this is a very exciting result. I mean, I think this is within range of coming up with a credible, reliable alert system that could be implemented in the, for these local councils who are spending a lot of resources, and resources in these councils are scarce, to deal with this issue. So we published this work in Journal of Flood Risk Management, and we've had feedback. No academic has just cited it, which is fine. But I've had calls from at least 5 camera producers and environmental consultancies who picked it up and were interested and are discussing how we can collaborate on this, which to me, is a quite exciting route forward. So to try to follow up on this, one of the criticisms we faced was like, yeah, but a logistic regression model, come on, that is so simple. You must be able to do better than that because there's so much, I mean, the image analysis group is big. So we tried with different, and I cannot remember the names of all of them, but these are other image analysis models of increasing complexity. So we did a bootstrap type analysis where we took the same data sets and shuffled it 100 times and tried to refit the models. And so up here we have accuracy on the y-axis, these different models here, and the box plot is the sort of uncertainty on the accuracy. And here in the green is the logistic regression, and these are increasingly complex image analysis models. And what you see is that, yes, it is simple, but it's pretty robust compared to these, and certainly comparable to the more advanced models. So take some comfort in that. So conclusions, it seems to work. I think we're in positions where I'm happy to say when we can detect blocked and unblocked from CCTV analysis, the results are robust. We are now trying to implement this a bit more, so we actually get an alert system where we can tap into their CCTV images and send alerts to their phone saying, yeah, do something, it's blocked. But also I think there's, on a greater story, I think there's scope for implementing similar systems in other parts of the world. I mean, cameras are small, they're cheap, probably becoming cheaper as we speak. These issues are not isolated to the UK. Huge issues with debris and trash across the world, not least in developing countries and large urban connotations and so. So I think there is a potential here for a cheap, manageable solution to help combat that. Then I'll stop here.
Thanks, Thomas. Just a kind of starter, I suppose. I had a couple of questions. I mean, I suppose, first of all, for you, Eunice, really interesting about what you're looking at. And this may not surprise you, the tone of my question, which is, it's great to see like that machine learning around the qualitative lived experience. How would we start to use that in a real-world context, do you think? You know, what's the next stage to get it to be something that, for instance, you might give to a public health professional and say, here's a model that will help you think about public health planning for the future? I don't know if you have any thoughts on that.
Yeah, very difficult question. I think perhaps instead of a health professional, we could definitely use this research to inform adverse weather planning. So one of the things I discuss a lot in the paper is that just looking at what is in the adverse weather and health plan for different public health agencies in the UK, and also what the Met Office suggests we do or don't do in extreme weather, and then matching up with what people actually do in their day-to-day life when cold weather and storms occur. And they do a lot of things already, but definitely some recommendations aren't really taken on, particularly on a lot of people saying that they reduced exercising because of cold and stormy weather. But actually the proper guideline is that if you don't do as much outdoor exercise, you definitely should move more indoors. That people might not have picked up on, or they probably didn't just think about reporting in a survey. But I think by comparing what actions we'll take up versus what are the official recommendations, we can see what messaging might be needed to be pushed more in these guidance when dealing with extreme weather.
Okay, so quite a practical thing about how you can actually modify, change the kind of guidance that comes around this so that you get more actionable things.
Yeah.
That's great. And Thomas, to you, I mean, there was a really interesting presentation, and we were talking about it before we came in, and you mentioned about this application for use in other countries. Now, I work a lot in Africa and Asia, so you're right, you get an awful lot of blocked stormwater drains. However, it doesn't tend to be trash screens, because it'd be great if they even had trash screens. Could you adapt this methodology that would be able to pick up those kind of blockage problems that were not related to that particular type of technology, but could be applied more widely across the stormwater drain system, do you think?
I think so. I mean, I don't see why not. I can't see there would be any technical barriers to do that. I mean, as long as the camera is sort of broadly looking at the same location in different circumstances, it seems to me that this could work as an alert system. That, of course, the alert system itself doesn't necessarily prevent the problem. There needs to be institutional manpower, etc., to actually do something about it afterwards. But assuming they have that, and it could perhaps help to direct scarce resources to where they're needed the most. I think that will be the aspiration.
So a follow-up on that has been, I suppose, how easy do you think it would be to train something on a different set of blockage-causing problems? Because obviously trash screens is quite, you've got a point in time you can really predict. So would you need to do some other training to think about your drainage system, do you think?
That's a really good point, and it's this one. So we have trained it where we had data, etc. And in this particular case, we had 600 images, and that takes time to build it up. And of course, you might not be in a position where you want to wait 2 years before the system becomes operational. And so we are, and we haven't completed this yet, but so if you train the model on this particular type of location, it kind of looks like this. It has this sort of structure. If I find something similar, can I somehow measure the similarity between locations, like some sort of clustering analysis, say, and then say, the model worked here, and this looks to a computer vision a bit like this. Can I port it along? And you can. We're talking, obviously the accuracy and the precision goes down substantially. So we're in the process of trying to develop a a system where you have the initial estimates, and as the images come in, you do sort of real-time update of the solution so that it doesn't need to wait 2 years, but it can adapt as it goes along, and hopefully that'll be more quick.
So quite a lot of potential, and certainly I can see there's lots of potential applications.
Yeah. So why it looks impressive on this one is because we have lots of images, but the real problem is probably where we don't have so many.
Yeah, that's great. Let me open it up to the floor. We have roving mics, so if you want to ask a question, if you could put your hand up, and I will try and get somebody to mic. So yes, this guy over here.
So I have a question, one question from each of you. Thomas, it's quite an intriguing, simple solution that you have on using cameras to identify these choke points. But one limitation could be that these choke points happen somewhere that the camera is not looking at. How would you kind of solve that problem? Because that would still disrupt the flow, and the cameras would be capturing that. But so for instance, one of the cameras would have increased flow of water, and the other would have nothing. But the choke point would not be visible. How would you sort of deal with that?
Do you want me to answer? That's a good question, and I don't have a good answer for you because it's such a good question. I think at the current state you would have to know about the system, which the flood manager, they do know where the sticking points are. I think the broader sense is that if you have too many of these cameras, they might be picking up the same event. Say the same storm comes in, and suddenly you're not dealing with one alarm, you're dealing with 10 alarms at the same time, but it's essentially the same problem. And I think I would love to talk to anybody who thinks this is an interesting problem, because that could easily be scaled up. And we're talking to water companies as well, who have very, very complex systems, thousands of sensors, and when something goes wrong, they get thousands of alerts into their operating room, and they don't know where to start with it. So this is it's a very good question, and I think there's still work to do here. Yeah. Thank you.
Yeah. No, thank you. And my second question would be from Eunice. With the extreme weather events, it's also part of research that's interesting to me. But with extreme weather events such as high temperatures or storms, one limitation that we have is access to healthcare facilities as well. So heat can have great impacts on sort of cardiovascular health and otherwise, but a lot of the mortalities sometimes appear in the data because of limitations to healthcare. How do you sort of manage for that?
Good. Yeah, well, I think, this is a great question. I think in mortality, I think that's probably less of a problem than looking at, say, GP appointments or diagnoses, because those are more affected by whether people get an appointment, whereas I guess mortality are more, serious things that we can pick up a signal in those large numbers. I think that's why my current thinking about using AI methods, perhaps something like knowledge graphs that I don't know anything about, but I'm talking to people who know those, can bring in a lot of data, right? So these can be, first of all, the weather exposure data. We have a lot of those weather observations anywhere, basically. But we can also bring in, for example, data for different towns where how many GPs and how many hospitals there are. And I don't know, if in a storm, we could potentially use transportation data to look at where there have been road blockages and so on that affected people's access to healthcare. So by using new AI methods that can bring in different data in completely different domains on completely different spatial resolution, then I think we can start to kind of integrate all of these things to then think about this problem, because as you said, my research obviously wants to look at what's the weather-related signal in all of these, but these are also affected by, is this town more deprived than the other? Are people in general are they older or have worse health outcomes, or have more exposure to many other things that aren't in the weather? And I think we need some new modeling technique that bring all of them together. I don't know the exact solution, but I think that's where the research will have to head.
think actually one of the things you could be using this for is how you start to actually define proper resilience planning across a whole system. Because if you start looking at that way, exactly, you can start doing those things like you said, Eunice. You can start integrating inequalities. You can start looking at differentials in a different way. We've got time for probably one or two other quick questions if people had anything. Yes, Mark.
So one of the challenges with sort of blockages in stormwater is obviously you've got the rubbish lying all along the channel, and then it gets washed down and blocks up where you have these grates or whatever. Any ideas on whether you can sort of trigger a general channel or upstream cleaning exercise when the load gets to a particular level? I mean, where I'm from in Cape Town, it's just routine that people go out before the winter season, and essentially there's a whole process of trying to remove that stuff. But, yeah.
That's an excellent question. Yeah. The idea is, so I've got a student working on this at the moment, is to, now that I know which images are blocked, I want to link this to, so I know when in time they get blocked. I want to link that to the causal events that happened, that caused this blockage to occur. How much did it rain before? But not only that, the span of the dry, warm period that would have come before that. So there's a time when it doesn't rain, where people just dump stuff on the side, or debris falls naturally if it's woodlands and so on. So I want to come up with an alert system that says, here's a weather forecast for the next 5-7 days. It's been dry this long. It's in the middle of summer. The probability of you seeing a block in the next 5 days or so is X%. Do something. So that is the ambition, is to take it from a sort of reactive saying, the image is blocked, and it's already blocked, to something that's a bit more proactive and anticipatory, and so it's likely to block. So that's we're working on that at the moment.
Great, thank you. Do we have time for one last question? If anybody would like to ask it. Yes, please, great. At least some gender balance.
With the blockages of the rubbish, is there a way to incorporate public reporting into that, so you don't have an over-reliance on machine learning or over-reliance on public reporting as well? Like an incorporate, I guess, includes both of your research then.
I'm sure there is. I wouldn't quite know what the system would look like, whether you could just say, I've seen a block, or report to your council that you've seen a block. We are working with people in South Africa to try to take the idea further, because they have working people in KwaZulu-Natal. They have a citizen science project where people take photos of things that annoy them in their townships, and so you get photos of burned out cars and rubbish, fly tipping and so forth, and people take images of it. The problem is they don't label them, so you don't know. They're angry about something. You're looking at the image and you're trying to figure out, wonder what you're angry about, and you discover that there's a burnt car somewhere in the vicinity, and they're very different cameras. Some are very cheap, some are very good, and so you get very different qualities. So this is proving quite difficult, but I think there's a lot of scope for doing, and a lot of interest as well. So I should say I'm also I'm a member of the Bristol Avon River Trust, and that's the same. Lots of volunteers in Bristol go out and look after a bit of river and take pictures, but again, they get angry about something. You say, there's a rubber tire at the bottom of the river, but it takes a long time to sit and sift through all of this. So smart people who can do sort of segment analysis or work out that there is a rubber tire or a Coke can or whatever it is in an image, I'll be very interested to talk to you as well, because I think there's a lot of scope for that.
Great, thank you, Thomas, Eunice. That's been excellent. Really good presentations, really good questions, really good answers. So thank you very much. And I can't resist it, but just say it's music to my ears that people say logistic regression works. It's always worked for me, I have to say.